Okay, that's recording. That's a good question. Why don't you use 4 phases? There's this amazing thing that happens with 3-phase specifically with regards to the number of wires that you use. I think in the slides they do speak about it, but basically you need 2 wires for a single phase. Then for 2-phase, I think you need 4 wires, but then for 3-phase, you can share the one. So you get four wires, and you also get 3-phase, and then there's like something special that happens with the amount of wires that you need for 3 specifically. Actually, there's a good slide in the intro slides they explain, and also the amount of energy that you get. You get more with 3. There's like the amount of wire you use and the amount of energy that you send. So that's 3. I did look it up myself actually, and I found out that in like it actually does get more efficient. So the more phases that you use. So there's these things where they need to heat up metal. Okay, and when they heat up metal, they're using such high energy that they really need to minimize the amount of like loss, because there's like a certain associated loss with the less phases you use, because you'll see that you get more and more energy. There's like, I don't know if you saw on the slide, there's like the half. I'll see if I can actually find it. But yeah, so for those heating applications, they used like lots of phases. I think they said like 30 phases or something crazy. So yeah, they do use more phases. It's just that the 3 phases is just that like sweet spot where you use the first sort of like big leap in the amount of energy you can transfer, and then it gets like diminishing. You do get more and more efficient, but it's diminishing, more and more diminishing past 3-phase, and then you have to use more wires, which is more expensive. So yeah, you can use more phases, but that's more or less why you use 3-phase. Also the asymmetry of it, if you like imagine turning a motor, if you have 2 phases, if you have like poles, I don't know if I can do it with the camera, if you have like poles like this, you can turn the motor between these 2 poles. But if you have 3, you have sort of a better sort of torque sort of thing, because you have 3 distributed. It's a bit better than a right angle. But then obviously you can get more and more and more. So yeah, it's like that first point as well. I think it has something to do with that as well. Okay, so that's one question. I'll actually do that a bit better. Yeah, please. So you must ask a question about the test, because this time the feedback's going to come like tomorrow morning, and that will be that. So it's quite casual, so we can speak about it now. So no deferreds or anything. Yeah.
Okay.
Go ahead.
Awesome. So in the test, it said from input to output, it takes a certain amount of time, and then in the test they called it capital T. Now, there was no input or output demarcated in the graph or mentioned before. I looked through like the notes and I can't find anything to do with input or output. So I was wondering, is that just like where x is naught and when x is alpha, which is the end of the impedance line, I think?
So I called it input and output, and you're saying you didn't see anything about input and output like mentioned.
Yeah, so I didn't know where exactly you wanted the input and output to be. And then I just guessed it was like the start and end.
Yeah, that is the input and output. If you think about you connecting a source to a load, you can kind of think of it as, maybe that is a bit ambiguous. Okay, I'll watch out for that, because perhaps, but it's kind of the input of your power to the output of your power to the load. So that was kind of the thinking about around that. So
Okay.
yeah, I hope other people didn't have that problem. I didn't. Yeah, is that kind of like justified? Would you say?
Yeah, then it asked what is the voltage when it travels from the input to the output, and then I was like, okay, that the first initial one is just V naught, and it was worth like 2 marks, but we had already calculated V naught in question one. But then I like double guessed myself, like, well, if I've already calculated this, why am I getting more marks for
Right.
it?
Let me look. Yeah, it's quite a bit generous. But let me just see. Yeah. So what is the voltage? That's at the load, and then so you see, so it's slightly different because the ones asking for the initiated voltage and the ones asking for the voltage at the load at that time. Now, at that time is the point at where the reflection occurs. So it will be actually different to your initiated voltage.
Now, is that before or after the reflection?
So good. Okay, this is a good question. Let me explain this. Share my screen. This is a very, very good question. Good. I did think that people were actually going to get a bit caught on this sort of concept, so I'm glad that I can actually show you guys. Let me actually stop my. Is my video still sharing? Like my actual face video. I think I'm gonna stop that. If it is. It is. Wait, let me see how I can stop that. Let's see, stop. Oh no, now my video is gone, okay. Because I'm gonna put my iPad down. Stop, let's see. Share my screen. Yes, no. Okay. This is my master's. Here we go. Just go week 10. Not an emoji. No, not over there either. Okay. So does everyone understand? The question was asking. It was asking. This was question number. What was it? 7. So it was just after we said that t is equal to the time from input to output. Okay, that's what they give you, and they say, what is the voltage? I'm just going to say at the load in brackets like this, when t is equal to that time. So what I meant by input to output is that if you have your transmission line like this is kind of the input, this is kind of the output. Okay, this is your transmission line, always 2 terminals like this, and then you had your input impedance, the voltage source, and then your load. Okay, let's call that RS and RR. Then, so T basically is that if you have a length over here, it's the time it takes to go from there to there. So I'll just call that T for the time. Okay, so before you're asked, what is the initiated voltage? Now, the initiated voltage, you know, is that voltage divider. If this was Z naught over here, you would just do the initiation sort of thing where it's actually deciding what is going to be the starting voltage, and it's going to be voltage division because of that whole thing that this beginning portion of the circuit, the reflections are happening so quickly that they behave like circuit theory because it's a small distance and it's just abiding by, yeah, so that kind of happens. It immediately agrees to circuit theory because the reflections are happening so quickly. So that's VO. Is someone going to ask a question there? I heard a mic. Okay, I assume not. So yeah, that's VO. So that's slightly different to V load. Okay, so they're saying at T, so that means the signal at t0 was over here. At t, the signal has arrived at the load. What happens as something applies at an impedance mismatch is that a reflection occurs at the exact instant that happens. So if you, that's when it actually happens. If it's less than, then we're over here. When we at, that's actually including the reflection. And if you draw the reflection diagram, remember, so I'll just draw the reference to the transmission line, which is showing the x. So this is what the reflection diagram is showing us. We have x on the x-axis and then time over here. So this is time, this is x, this is our transmission line and the distance down it. For example, over here means that we are over here in the transmission line. Over here means we are over here in the transmission line. So actually the beginning would actually be the beginning over here, but it's not drawn perfectly, but yeah. We say that a signal travels at t equals 0. So over here on the vertical axis, t is equal to 0 and x is equal to 0. If we drew a point here, we would see that t is equal to 0 and x is equal to 0. If we move along this, no, x is not equal to 0, x is equal to, we'll call it L for load, for the length. So then this thing has a length of L. Okay, and then like here, for example, with this yellow one, that would be like half L, for example. The x would equal to half L. Okay, so now we're going to get a wave that's going to move, and we're just going to draw it like this. So it's progressing in time. Can you see time's getting greater? And it's this is, so you see those arrows are showing, let me do it in pink to show that over here time is progressing. So we're progressing in time as this line goes downwards like this, and then we're progressing in distance as well as the line goes to the right. So that means if we label things with respect to t, which was that distance, we'll say the transit time is actually the word for it. T is equal to transit time. Okay, that's the time it takes to move across it, to transit across it. So over here is your delta t. This is t is, sorry, I don't call it delta t, they say that as well. They can also call t, this thing delta t if you want. Okay, but we're calling it t. So over here, this is a value of t. It takes that long, because remember the vertical axis is time. It takes t seconds to reach the load. Okay, and now what will happen if we just continue drawing this diagram, it's actually going to take, if we draw from that time, it's going to take another big T seconds to get there. So from here to here was T, as we see already. If I show it in like green, the 2 points over here and over here is the same distance as from over here to over here. That's 1 T. Then we have another T to come back from over here to over here. Okay, so then it's asking for the voltage at the load when T is equal to T. So now, when T is equal to T is right over here. And it's saying at the load, which is right over here. So we get this point. So the voltage at the load is going to be equal to, we'll just call this gamma L for the reflection coefficient from the load. Okay, it will be equal to the sum of those two things. So it'll be the one that's coming in over here. It'll be both of those. So it'll be equal to V naught plus by V naught times by the reflection coefficient. That's the value at t at exactly that time. Because you actually, yeah.
Why is it exactly at that value? Like if I take an infinitesimally small value to the left, right?
Yeah.
Like t tending, like 1 over t, and t is tending towards infinity, right? Just that much less time. Will it just be V naught?
If you say, we have 3 different options here, okay? So we have t is less than t, we have t is equal to t, and then we have t which is greater than T. Okay, at less than T, it's 0 volts. Okay, so let's just draw that voltage signal. It comes, and then the thing is that actually what happens, okay?
Is it not
so
V naught, or is it 0 volts?
it's 0 because it hasn't reached there. If it's just before, it's 0 volts. Think about it. So if I say what is the voltage at it's less than T, so can you see if I look at this graph, this wavefront hasn't arrived here. What was on the line before was 0 volts. It was discharged. So that's what. Yeah. So this is very important. I'm glad you see this now, not in your exam. And it is tricky. But the whole reason why it is both of them is actually, if you do, you'll see that there'll actually be now a voltage that will be transmitted that's equal to the sum of these two things. Okay? I'll just draw the load resistor here. This will be like what's transmitted to the load. And what actually ends up happening is that the reason why we get this, one way of looking at it is the reason why you get this reflection is so that the impedances on each side, so if this is your transmission line, you'll get a voltage and a current, and you'll times them together, and actually, for both of their ratios of V to I to exist, okay, they both enforce that they have to have a certain ratio, both of those things, and also we need an extra thing of energy conservation. And to maintain energy conservation, for it to have this sort of ratio, for them to both have their desired ratios, you actually have to create a reflected wave to ensure that happens. There's a derivation again in that appendix of my master's where I speak about this sort of conversion and this this conservation. So that's why at the time exactly it actually can't be just V naught. It has to be V naught plus by gamma V naught. It has to be that because it actually, if it was just V naught, it would not agree with these two ratios. That's actually how you can justify that there is a reflection. It's very weird, but that's one way of deducing it. Okay. So does that answer that question? At the time, it's both of them. Can you see? Both of them. Be aware of that. So then at what time would it be V naught? It can never be V naught. It isn't V naught, ever. You could say just before, but it's not even just before. It's like the value, it just isn't. As it interacts with that sort of impedance, it enforces that condition immediately. For it to even interact with this thing, it has to enforce that. You could go into the fine sort of thing and be like, okay, well, maybe when it was halfway here before, but then we're not saying that it's at the time that it's interaction. So that's it. It gets into this weird sort of space. But when they say that, they mean that it's both of these things. That's why it's a point. It's a point that has both of those. So be very careful of that. I do understand that that is a slightly tricky thing, but yeah. So it's never actually V naught. It's only that. When it interacts, it has to be both of the forward going and the reflection wave. I could say if you wanted to get an answer to be V naught, I could say what is the incident wave at the time t is equal to this big capital T. I could say what is the incident value of the incident wave. So this I could call the incident, and then this I could call the reflected. And then that's how we would get a value of V naught. You'd say the incident wave is V naught. But the actual voltage there is the sum of the incident and the reflected. Wait, there's a long question here. Quick question about the whole Tesla versus Edison contest. I'm not sure I understand how Tesla can be the only winner here. I understand that the more losses go over longer transmission line, but can't Edison's DC voltage use transformers in the same way that Tesla's AC voltage use transformers to step down and step up the voltage at the appropriate distances in power plants? As if maybe I'm not getting this thing. So, well, immediately you have a problem with the distance of the transmission because you get losses with respect to current. They're called your copper losses. So with DC, you need a higher current to allow this because you can't actually use the transformers so effectively. Remember, if you have your transformer, is essentially two linked coils where it's literally like gear ratios, okay? If you have like one big gear and one small gear and you connect them, it's exactly that sort of thing. One will move faster and have a low torque, or it will move slower but have a high torque. You're doing a conversion over distance and time, but you're conserving energy to have one of those. So you just amplifying one of those. But remember, this actually has to be alternating. In order for you to create a field, you have to have a change, okay? If you remember, you have to have a change. So this, I'm just going to draw it like this in both ways because it will like oscillate. Remember, it was Faraday's law. The voltage is equal to the change in flux over the change in time, negative n. Okay, d flux dt. So if you change a flux, so this is your magnetic field. If you change the magnetic field within a loop, then you get a voltage, only when you change it. If I hold a magnet, okay, so why we care about the magnetic field is because this is actually the magnetic field produced by the current moving. But if I have a magnet, a stationary magnet like this, so now we're going to say the magnetic field is not produced by an alternating current, but rather it's produced by a magnet. If I hold this magnet by a coil like this, I'm actually not going to get a voltage across this. It's not going to happen. The only time I'm going to get a voltage is if I change. If I move that magnetic field, I change it, then I'll get a voltage. So you actually need AC to make that voltage. So yeah, so your whole transforming sort of things don't work because you can't actually induce a magnetic field with DC. Well, in modern converters you can, and they're called, they like, that's actually part of my master's, is DC to DC conversion. They're a whole set of things you'll learn about, and very big with charging your phones and everything. But actually how they work is that they send in pulses. So this is a DC pulse like this. Okay, and this will be your signal. So it'll be on and off. Remember that this is just like, let's say like 5 volts, which is a DC value. This is 0 volts. But essentially, what are you doing? You're kind of changing it. So yeah, that's kind of why. There's definitely a place for DC. You have to give credit to Edison. He was definitely essential to everything. It's just that everyone thinks a bit negatively on him because he was quite like a business sort of tycoon guy, and he was known for being like a bit hectic, like a hectic businessman, and he was like short doing people and stuff. Like he challenged Tesla to rewire his whole lab, that he did, and then there was a whole dispute about him actually getting paid for it. So I don't know. That's also why there's a negative look at Edison. Okay, was there a question coming there? Wait, as far as I know, we can't get to use it. Transducer require. There we go. Look, that's exactly what I said. I think you said this a whole long time before my whole explanation. Okay, well, there we go. There's your question answered in like 5 minutes ago in one sentence. Okay. What's next to be discussed? Also, today's tutorial is not going to be so long because, man, I still need to do my presentation. It's been hugely stressful, man, making all the exams and this quiz, and like these, whatever, personal life problems. But yeah, I just can't stay for long is what I'm trying to say. Like gaming. Okay. Any other things you guys would like to discuss? Any thoughts on delta and y? Have you guys gotten that far? The concepts of delta and y. They look a bit intimidating. Maybe I'll just speak about them quick for myself. Well, just because I think it's important to kind of address this. We have delta and y. Delta looks like a delta sign, y looks like a y. Okay, you can also call this star because it looks a bit like a star. Basically, you need 3 y's, okay, for 3-phase. Both of these produce 3 y's. This one has like a 4th neutral wire. You theoretically don't even need that 4th wire, but you do have it for like a return. But yeah, you have three wires, okay? And you can extract power or send power across transmission lines in these sort of like 2 techniques. Now, I wonder if there are more configurations, but it's quite hard to see, specifically if it's this thing called balanced, where everything's symmetrical. I'm not so sure. Let's say you have 3 segments. Let's say that our sources are voltage sources, okay? We'll have V1, V2, V3, and we want to make something symmetrical, okay? And we want our output to have 3 wires, let's say, 3 live wires. Perhaps we want to, maybe we can introduce a 4th for a return, okay? But if we have these 3 things, how many ways can we really connect them? Let's just copy them. That's symmetrical as well. Just paste it a few times. So the first thing you think about doing is you connect it like this, and then this becomes 1, 2, 3. What is this? This is this connection in the middle here, so where I've drawn that pink line, and then these are your 1, 2, 3. That's why. Okay, and then we're symmetrical because if we see at the base of each line, we have the same thing happening. Cool. What's another idea? Well, you could, let's maybe try something like this. We connect this one to this one. We connect this one to this one. And let's say we connect like this one to this one. Okay. And then let's see where we'll make our outputs. We can say maybe, let's just see, we do one over here. Let's think about it. Do maybe one over here. So there's a line in between each one, and then that will do one over here. Okay. And then if you look at what we've actually done here, so you can see that this is symmetrical. If we follow the path from one terminal to another terminal, we can see we go across one voltage source, and then we go across another voltage source. Cool. Let's see this from this terminal to this terminal. Okay, so we've done something wrong because that can't be. I can't draw my wire here. I have to draw it. Let me just see how you can do this. If we draw it over here, there's a way. Well, there's a way. Basically, I'm trying to do it in a very weird way, but you'll actually get exactly. Let's just see if we can figure this out. From that to that to that, which is essentially the same as going. I'll just draw one like that. We'll draw one like that, and then we'll draw one like that. Okay. Do you see that that's the same thing? Then let's see where we'll draw our wires for it to be symmetrical. We'll draw one here. We'll draw one here. We'll draw one here. So it will literally be at every. Okay, so you'll draw your one wire here. You'll draw your one wire here. You'll draw your one wire here. And then we have everything symmetrical again. What else can we do? What is another way of doing this? Can you see what I'm trying to do? I'm trying to make sure that between each of these 2 things it's balanced. What else can we do? Does anyone have an idea? To maintain the symmetry, because the symmetry is important. You can make it unsymmetrical, and then probably there's a whole variety of things you can do, but these are kind of the 2 basic configurations of 3 energy sources. I don't know what else you could do. So yeah, this is where we end up with delta and y. Basically, they're both balanced, and they're like the configurations that we can use, and they can interact with each other in different ways. Has anyone approached that square root 3? Have you guys been looking at these three-phase things at all? I do understand if you haven't, but have you been checking the square root 3? Does anyone want to explain the square root 3? If you know what I'm speaking about. There's a square root 3 when you go from, so basically what's going to happen is that we end up connecting these two things. So these delta and y's can either be the configurations of our sources or the configurations of our loads. It can be either one of those two things, because it'll be three-phase. There'll be a three-phase load and a three-phase source. So you can make either a delta or a star. You could make this either delta or star. You could make this either delta or star. So then you start to get, if you consider the convention of load, from load to source, from, oh, not load to source, from source to load, you get all of these different things. And they say it in this way. They'll say a delta y configuration. They could say a delta to delta configuration. They could say a y to y configuration. And they could say a y to delta configuration. So you could connect your sources to the same thing, to the opposite thing, and it doesn't matter. You can do that. Like, I think motors generally, you connect it in delta. And there's reasons for it. I think it has something to do with the current. I can't think offhand actually exactly. I wasn't super prepared for three-phase. I actually did make a whole, I should actually check on my computer if I can see my notes in three-phase. I did a review. A whole review of three-phase. I'm just seeing if there's anything that I can miss. Just look. I'm just looking on my computer. Okay, no, that's fine. Okay, let me go back here. Okay. So yeah, that's how you can connect your things. Oh, yeah, what I was actually looking for is if there was any benefit of the two. We can logic it out ourselves if we want. Basically, there's the main difference between these two things is that if you look, I'm just going to draw. Okay, let's look at a star one. Okay, like this. If you see our line, so let's just consider line to line is a convention, what we call line. So if this is a line and this is a line, we'll call this voltage V line to line. Okay, then there's another thing which is your phase. So this over here is your phase. Okay, and now these two things are going to, and then okay, wait, there's the last one. So then this is your current of your phase, and then this is the current of your line when it's actually on the line. And you'll see that there's all different things. So let's just draw the delta next to that, and we'll just draw our two lines because that's going to how you compare them. And this will also be plus minus V line to line. Here we'll have plus minus V phase. Here we'll have current from the phase, and here we'll have current on the line. And you'll see that something different is happening to each of them with respect to voltage and current. Here we can see that the phase, let me draw this in blue, the phase current and the line current are exactly linked. They're actually exactly the same. You can say that I phase is equal to I line. With the delta, we can see that V phase, if we see that it's between these 2 points, can you see that this is also measuring those same 2 points? Conductors disconnect. You can always shrink conductors if you're not considering their travel time to 1 point. Remember that whole nodal sort of analysis. A node in a circuit, if you have like a resistor and then a resistor and then like a long wire and then a resistor and maybe like a voltage source. This whole thing here is considered a node. It's arbitrary because the distance, you don't actually account for any distance, any lengths in circuit theory. I don't know if you've noticed that, but you've never taken account to geometries. You can do all kinds of things. You can draw your circuits in different ways, where you draw them like maybe more neatly next to each other, and then the one goes off there, and then like you box it or whatever. And that's because we don't care about distance. We only care about nodes. We look at currents at nodes, not at exact positions. They're arbitrary positions. So yeah, that's why over here, can we see that we're measuring the voltage of a phase? That voltage source over here is enforcing that the voltage must be itself. So over here, we have that V phase is equal to V line to line. So that's where they're the same. Where they say that the voltage in delta is the same as the line for the phase, and then the current in the phase is the same as the line for the star. So wait, there's someone's mic. Wait, I can mute you. There you go. Okay. We can look at voltage. Let's look at voltage over here for star. Over here, and we can see that there's kind of two voltage sources between it. This will be minus and plus. So we'll know that V line to line will actually be bigger than V phase. Okay, and we can kind of see over here that there's like the current's not actually facing this way, but because we're dealing with sine waves, it doesn't really matter. We can just see kind of that I line is greater than I phase because it's the sum of those two things. And how exactly greater is it? It's by square root 3. Is the exact quantity it's greater by. Okay. You can derive that in a beautiful way. We'll maybe do this. You'll see there's complicated diagrams. I don't know if you guys have seen that in the green book. It's like this diagram, and then it's like makes like they have all these vectors and then like stars. It's like this crazy thing, and it looks very intimidating, but it's actually very, very easy. Let's do that for star, just for fun. Before I go on, is there anything else maybe you guys want to do? Because this will be quite a portion of the time that I'll be going. If you want to maybe ask something else, I can maybe focus on that. Or should I just do this? What do you guys think? Just say, well, okay, I'll give it like a few seconds. Let you guys think and think a little bit more. Then like time to type if I see typing. Okay. I don't see typing. I'll do it. So to start, remember we have 3 phases. What are phases? Phases are your voltage sources. So before, where we had like a single transformer sort of circuit, remember that like sort of equivalent circuit, that was basically a 1-phase circuit. Okay, this kind of looks like the transmission lines, like 1 phase. Okay, what we're going to do now is we're going to connect 3 of those phases. These 3 voltage sources, we're connecting them together. So, and we do it in a very particular way. We say V phase 1, let's call it A, is equal to, we'll just call it the magnitude of the phase, which we'll just call VP, and we'll have an angle of 0 degrees. So we're going to just say that this is our reference one. We'll call phase A our reference phase. Okay, then we'll call, let's just call this V A, VB, and VC. These are going to correspond directly if we have something like this, and we give them, remember the notation of plus and minus just has to do with where you are in your phase, if you know what I mean, because it will repeat. So it's just saying that it starts at like it's across the positive term. This is positive. You know what I mean? Like that's positive. Okay, and we can call this, I'll just put an A, a B, and a C. Okay. What is the most symmetrical way of connecting all of these things? If we're going to give them a phase shift, oh, no network. What happened? Can you guys still see what's happening here? I disconnect.
We can hear you, but we can't see your screen or anything.
Okay.
Or I can just see the team screen, if that makes sense, with you showing the team screen.
Oh, I think I just stopped sharing. Okay, let's just, I'll do this one quickly just so you guys can, when you see it in your notes, it'll be a little bit more meaningful. This will be minus 120 degrees, and this is VP minus 240 degrees. Okay, so we set them out of phase. If you were to draw that in time, each of them on the time axis, so we're going to measure each of them over time. So at like t equals, if we have time over here, and we'll have voltage, and we're going to measure across each of them. So the measuring will be like this, for example, will be phase A. We'll call this from here, from exactly like this, plus and minus. Let's just say it starts like this. Okay, whatever. Then let's do the next one, B. Okay, this is going to be 120 degrees. So if that's 90 degrees, then that's like, I don't know, it's like a bit off, whatever, something like this. Okay, and then just fill it out. And then the last one will be like a plus minus like that. And it'll be 240 just before this one's 360, something like that. And then you get these three waves. Okay, I've done it not so well. But anyway, you have these three waves. Let me see if I can actually get a photo. Cardi B. Let me get one maybe on my computer. Okay, whatever. Well, it's these three distributed waves. Basically, they go all on top of each other nicely. Oh, it's very bad. Okay, anyway, they just all distributed. They'll make like a kind of like a flat line here. They'll all have different times at the peaks. And then they kind of like fill out the line. You'll see it. It's like not gaps at all. If you look at two phase, for example, if you just had two things that were like 180 degrees shifted, you'd get something like this. If it was 180 degrees, because that's how you divide it by 2, you get one that's like this, and then you would get one that started later, 180 degrees later. So we'll just do it. So you get something like that. And can you see that there's nothing to fill in this gap over time? That's one of the reasons why three-phase also, it's like something to do with that you're filling up everything. There's not this waste in power. So anyway, we have these three things that are shifted. If we're to draw them as phases, this is our phasor diagram. This is our axes. We could draw this one at 0 degrees of a certain magnitude. Notice they all have the same magnitude. Can you see that? They just have different phases. So that this one have a length of VP. So if you measure its length, it would be VP. We would draw one at minus 120 degrees. This is in the negative direction because remember that's positive. And the way you know that it's positive is because this is x is positive and this is imaginary positive. So that kind of makes sense that you go in that way for positive. That's, I think, kind of the reasoning behind why we call that anti-clockwise direction positive. Let's draw phase B. Let's draw phase C. Okay. And they're all, so you see, they're all symmetrical at this point. Now we're going to start formulating what is this voltage here. We want to know what is the voltage of the line to line. And it's also going to be a sine wave, amazingly. When you add two of these things together, you actually get a sine wave. There's a whole crazy things of like all the trig identities you can see in this sort of math. I think we have a lot to owe to Euler, because the fact that we can even draw causes and sines is exactly this reason. Cos theta plus pi I sine theta. This beautiful formula. I don't know if you guys actually know. I'm just going to go off in a little bit here. I don't think you guys do. I don't know if you know how amazing this is. This is the gem. They call it the gem. I've heard lots of people call it like the one of the greatest discoveries of human like intelligence is to link all of these things. This is a mathematical constant, irrational, not even irrational, transcendental, which means even more than irrational. Look that up, transcendental. Then you have E. I don't know if E is transcendental. Also a mathematical constant, not a physics constant, a mathematical constant. Think about that. And think about what irrational means. Irrational means like you can't write it as a fraction. That means its decimals like keep on going forever. Okay, pi's decimals are so three. I don't know if one. I don't know. I literally don't actually know all of them well at all. But they're so random. The order they literally pass the test of randomness. So what they do is that this carries on going to see if there's a pattern in the decimals, because if you can see the pattern in the decimals, then you solve it. But it turns out if you see a pattern in the decimals, you can write it as a fraction. They take samples of these digits. Okay, let's say like 40,000 or however million digits they do, and they take samples, and then they calculate how many sevens do they see. Well, they calculate for all of the numbers. How many ones do they see? How many twos do they see? How many threes do they see? How many fours, fives, sixes, and sevens, eights, and nines, and then you could say 10, but we'll just do these ones. Just to see how distributed they are, to see if there's like a leaning towards something. And no, there isn't. They're completely evenly distributed, which means that it's like a test of randomness, because they're trying to see is this just like, how can we do it? But yeah, they passed this test of randomness where they all actually have equal probability. So anyway, you take this transcendental number, you raise it to the power of another irrational number. I don't think it's transcendental. Remember, this is the one where you derive it, you get itself. So that means if you look at its graph, if you take the gradient of this graph, okay, and you draw it, okay, so you'll say that this has a certain steepness, okay, and that will be the height of the graph, how steep it is, remember? And you do that for all of the points, you get exactly the same graph. Okay, that's quite amazing. That's why E is just, it's like the identity of exponentials. You raise these two things, you put them to a power. What does it mean to put a number to a power of an irrational number? Remember, we know powers like x squared means we must times something, x times by x. Okay, cool. If we have x to a half, that means it's like the square root of x. We're kind of doing the inverse. You times those two together, you get x to the 1. It's like the inverse of each other. You get the thing you started with before you did it, which was x. What does it mean if you raise something to pi? X to the power of pi. How many times must we write x? What does that mean? You must write it. It's very like maybe some forms at the top, and then you square root a little bit, but it's infinite. Okay. You make this an irrational number, e, and no, that's not it. That's not all. We put the imaginary number, which is the square root of -1, okay, which was good for to find out all the polynomials. You put those together and you get -1. So these are maths numbers. They don't have, they know like the physical observation almost, or they kind of are, but anyway, that's this. That's what makes this over here, this e to the I pi. That's what allows us to do phases. What a rant. Yeah, I really, really like that. It's really beautiful. Anyway, here we go. This is VA. This is VB. This is VC. Okay. We want to find out what is the voltage line to line. What we are drawing here. Let me just draw it again. What is the voltage line to line? Let's just draw it like this. 1, 2, 3. We want to find the voltage from here to here. If this is A, and let's say we're doing B, we want to find from here to here, line to line. And we'll say the positive side, we'll say from VA to VB, if we call these sort of terminals. Okay, let's see what happens. If this is plus minus, plus minus, plus minus. We kind of have to add the two together, it seems. Just double check that I'm not going to make any sort of space, any sort of mistake here. Just double checking. VAB. Okay, yeah. So then if we want to know the voltage from A to B, that's the same as saying from VA to B is the same as saying from VA, whatever VA is, minus the voltage of VB. Okay, because remember, if we have like voltage A, which is, let's say, this much, I'll just draw it as a bar, and then we have voltage B, which is this much. Okay, we'll know that VAB is kind of the distance between these two. VA, VB. So you minus the two. Do the minus and you get that. Okay, so if we have VA minus VB, we can see that minus VB is written, it could be like the negative. It will be on the negative. So if we see here, it will be like here. Can you see? That will be minus VB. Okay, and now that's the same as saying VA plus pi minus VB, just so that you can see that we're actually doing addition of the negative one. We add these two together, and then what we're going to get, if we add these two together, we'll do the parallelogram rule. So let's just make that clear. So let's do this one just in solid. The parallelogram rule, which means that we're putting this one on its end like that. We're moving this one to there. Okay, like we're adding them together. Or you're moving this one. You could say you're moving the negative one to the head of this one. That's what the parallelogram rule is showing. And we're going to add them together. And then we get this one over here. That's the resulting phasor. This phasor here is VAB. Remember, which is VA minus VB. Now let's quantify this. Can you see that it's longer? Okay, it's longer than the two together. This is one of also the big benefits of using multi-phase systems, is that you get a higher voltage than you do for an individual phase. Okay, but let's actually calculate the length of this thing. Okay, so let's just say, let's draw out this triangle. We're going to redraw this triangle where we have VA over here. I'm just going to draw the lower half triangle. So I'm going to redraw just this bottom half like this. Okay, VA, VB, this is minus VB. remember to make it on the other side so they're facing kind of in a similar way. And this is VAB. Okay. So we know that these are kind of equal lengths. Okay. So we know that these angles are equal. Okay. Now we need to find some sort of information about angles. Let's see what we can do to find angles. Okay, so we know that from here to here is 120. Okay, we know from here to here is 60. Okay, so then we kind of know that from here to here is 60. Okay, does that help us? Let's just check. Yeah, it's 60, and then you have the bisecting one. Okay. So 60, 60, we know that opposite angles are equal in the parallelogram. There's a way better way of finding this angle. How do we find? Oh, we know. Okay, we can find, okay, if this is 60 over here, then we know that the angle from here to here is 30, because it must make 90 degrees over here. Okay, a bit of a mess. Don't worry. So if we know that that is 30, then we can kind of say that if we were to draw over here, we'd kind of know that this is 30 as well. Is this helping us? 90 degrees here. I'm sure I did this in a way better way in my notes. Okay, whatever. We can literally can figure it out like this. You must try for yourself for fun. From first principles, do it. You'll see it will be so fun. Okay, let's not do it this way. We're going to just leave it that we had it at 60 in blue over here. We do know that these two triangles, let's just draw them in pink with a dark color because we can't really see what's going on. We know that these triangles are actually exactly the same. Okay, if these triangles are exactly the same, because remember that these angles are equal because the sides are isosceles, and if we know that this whole thing is 60 degrees, then we'll know that one of them is 30 degrees. There we go. We get 30 degrees. This is equal to 30 degrees. Okay, cool. Then we know that this one's also equal to 30 degrees. Perfect. Let's find the length of this side. You can kind of draw a bisecting thing. Let's draw this at a right angle. I think that will be good for us. A right angle. So now if we draw this triangle, this is often when I'm studying for these sections to teach you guys, this is what I end up spending a lot of my time doing, is just drawing, just fiddling around and making these things. You should try. I promise you, if you want to understand things, just pretend like you are the person that is as good as whatever human invented this, and then that you have the confidence to even investigate it. That's actually how you can do it yourself. Just have that arrogance, and then you might get lost, but you probably will just learn something about it. But you don't need to just learn it off by heart. You can actually make your own sense of it. Okay, so that's 30. We know that this is 90, so we know that this also must be 60 to make 180 degrees. There we go. So we could say, we could find this side over here by saying, we don't know what half VAB is. We do know, let's say VA cos, let's say VA cos, we'll say sine. Okay, so we'll say VA sine of 60. Okay, so sine of 60 is that one there, is equal to half VAB. Okay, now let's just see what sine of 60 is. I'm sure it's one of your identities. Well, I definitely know it's one of your identities. So sine of 60 is square root 3 over 2. So here VA, I'll just write in white now, square root 3 over 2. is equal to a half VAB. Remember, VA is your phase voltage. It can do just the magnitude we're dealing with here. Therefore, VA square root 3 is equal to VAB. Perfect, there we go. So basically, back to here, that mess, where I said it was bigger, that was the line to line, remember VAB, this was VAB. We knew it was bigger. How much bigger? Well, actually we have to times this by square root 3. So VAB is equal to square root 3. Remember, square root 3 is bigger than 1, so it's going to make it bigger. Square root 3 is roughly about 1.732. Okay. And then this is VP. So it'll be slightly bigger. Okay. There we go. Then you can do a similar sort of deduction for current. There's also just a slight thing here that we can actually find that, can you see that it's at an angle of 30 degrees? So we'd actually say, wait, let's just draw that thing again. I'll just draw the three phases all in the same color. Then we had that -1 there, and then we had the sum of that -1. We know that this is 30 degrees, and we know that it has a magnitude of square root 3 of VP, or VA, whatever you want to call it. There we go, it's bigger. It's a bigger circle than this circle. So there we go. By connecting those three sources, we get a bigger voltage. Now the reverse thing is going to, therefore, for the delta one, that's going to happen for current. And there we go. So now, yeah, that's kind of where we are. If you look in your green book, that's what they're doing. Don't be intimidated by those massive things. As you see, I'm so scared to share my screen. Let me stop sharing my screen just so I can show you the cool little triangle that I made. The only reason why I'm scared to share my screen is because in my exam preparation, let me just see, I like write about like ideas of questions, and I don't want that to be in the recording. I hope I turned off the recording because I'm looking at all the things now. I want to just show you the cool diagram in color because I don't think they show all of the options. Here we go. Imagine you just saw the exam. So risky. Okay, here we go. The exam in sight. This was kind of the derivation that I did in a slightly different way. This is doing those negatives, and then you add them together, and then look at this amazing thing that comes out. This is if you do all of them. So they only do parts of this, but if you can find not only like they only do VA, B, V, like B, C, and VCA. Those are the three you deal with. But you also actually have VBA, you have VCB, and VAC. So that's when you get this cool star, which is really beautiful. And I was drawing it just roughly. So there we go. I think that is good enough for today, unless there's any final closing questions or anything. Don't know if that was useful at all. Just kind of went on there, but yeah. Any final statements? Wasn't a terribly structured TAT. I will give it that much. It was kind of all over the place, but yeah, forgive me. It was quite a hectic week for me so far. So yeah, I'll just give a little bit of time here for you guys to think about any questions. If anything I said made sense at all. Did it make sense? Anything that I said in that three phase, did it help at all? Are you more confused? It made sense. Amazing. Okay. Well, there we go. I'm glad that I didn't completely just speak. When I just go, man, I'm just thinking all over. It's like when I don't plan specifically, and then I just like I'm a bit ADD. So like, I want to ask a question on the test. Ask quickly, yeah. I'll do this last question. Then I have to go do my thing. Let's hear your question. There you like. Oh, there you go. My question is, they ask T is the voltage. Yeah. What about that? You want to know what they mean by that? Oh, I can show you. Let me do that for you quickly. This will be good. Wait. Let me just go to the right place in my OneNote to not accidentally spill the beans on the test. Then do we take the reflection? Look, okay. Let me show you. Good question. So they're asking for the voltage at which side? What do you want? The voltage of the load or the source? Maybe both. I'll do both because it'll ask for both. So we want the voltage of the source side and the voltage at the load at t is equal to t. If you're to write your function like this, v, x, and t, then these things would be like v, I'll say s for the distance of source, which will be, the x value will be 0, the t will be, oh, we want 5t as well. The notation would just look like this, 5t, and this one would be the v, the distance of the load r, or we could put 20 there because we know it was 20 meters long, and we'll put 5t over here. That's how you just write it for these two things. Let's draw, so the best thing to answer this type of question is with a reflection diagram. Here we go, similar thing. Remember this is x, remember this is time. Understand that, please, that you know that this is x and time. That really makes sense, and if you know that what that means, then you can infer the graph in whatever way you want. We have this sort of structure of reflections. So this is the other thing you need to know about reflection diagrams. We'll have a wave that travels like this. It will come back. It will go there. It will come back. It will go there. Keeps on doing this. It gets smaller and smaller as it gets times by each reflection coefficient, which is a magnitude less than 1. So it gets smaller and smaller. Converges to circuit theory. Okay. So let's say at 0, this is similar to the question I was asked earlier at when the time t is equal to t. Remember, okay, so this is going to have an impact here. So when I write these things on the side here, I'm referring to the time. Okay, so this is at t is equal to t. Over here, this is t is equal to 2t. This is equal to t, so I'll just say here, t is equal to 0t, t is equal to 3t. This is t is equal to 4t. Here we go, and we'll stop here. T is equal to 5t. Okay, I'm going to say the reflection coefficient of a wave coming from the input to the source. So from input to source, or I mean from input to load. Well, we'll say from source to load. From source to load. We'll call this L. We'll just call this S. Okay. We'll know the magnitude. We'll just call this as V naught, which is that initiated voltage, which is that voltage divider using the transmission line's impedance as the focus, as the voltage we want. we'll know that the magnitude of this reflected wave is times by that coefficient. We'll know that this reflected wave will get times by the source one. Now this one will get times by the load again. This one will be times by the source. This one will be times by the load again. Okay, and we could do one more, but we won't need it because this is further in time than we're concerned with. There we go. So those are all of our reflections. Let's see the voltage at T is equal to 5. Okay, let's start. We'll do the source first, at the source side. So if you're looking at the source side, that means it's along this x is equal to 0. And if we're looking for the load one, that would be x is equal to 20. We'll just say 20 for the actual meters. That was the length of it. And that will be down this line here, the x line. Okay, this is the source line. And now we want t is equal to 5. This is what we're concerned with. So this is the kind of time we're dealing with. T is equal to 5, like this. Okay. So what we're dealing with the source is this point here. Okay. And we need to see, okay, so well, what is the voltage at that point? Has it, let's see the last activity it saw. So we go back in time. We're seeing the last activity it saw. The last activity it saw was over here. Okay, that was when this wave came in and got reflected. Now nothing has happened there. It hasn't gotten changed. The next time it will get changed is when a wave arrives over here at t is equal to 6. 6t. T is equal to 6t. That will be the next change it will see. It only sees, the last change it saw was at 40. Okay. So there we go. So let's say, oops. We'll see, okay, for the source, it's going to be, let's just label these 1, 2, 3, 4, and 5. Then we would know that it would actually be the voltage of the source at 5t will be equal to, I'm just going to take, it will be 1 plus by 2 plus by 3 plus by 4 plus by 5. Okay, cool. Now, so then you'd add all of those up, whatever their values are. 1, 2, 3, 4, 5. And you see why you include 5, because it's that point, is what we're concerned with. Let's see the one for the load. So I'll just say load, it's a bit confusing, so use it for the transformation thing, but whatever. Let's just label this last one 6. Can we see that we're dealing with this point over here, and we're adding up all the things that have happened in the past? Okay, so that's 5 and including 6. So it's the same as everything except now it's going to be including that 6. Because you see all of those lines have interacted with it. It's interacted with 1 and 2, then 3, then 4, now 5 and 6 immediately. So at that time. So then it would be 1 plus by 2 plus by 3 plus by 4 plus by 5 plus by the newly reflected wave 6. There we go. And then that's how you'd find them. Yeah, that's how you'd find those voltages. So it's that same question before when I asked when it was equal to t at the load. You see you had to know to include both of those because of that sort of thing. That's just one of the principles of these reflections that I think is kind of justified, because can you see at this time there's two things happening. So it is actually both of them at that time exactly is when they're happening. So that's how you do it. The whole point of that is that you would have gotten some answers and they would have been very similar. Like I think it was 10 point something and then like 11 point something, I'm not sure. And then if you're to actually do the voltage division, the steady state circuit where you just had RS and RL, the steady state circuit, you'll see that the voltage over this will also be like 11 point something. It converges. These things are converging to this value. That was what I was trying to show at that question. But at 5t, the voltage is at the load side and not the source side. So that's just the wavefront. The wavefront, remember what's happening here. We have a wave that is traveling, that's setting up a voltage like this. It's traveling, it gets to a reflection, then a portion of it gets reflected. Then it comes back. Okay. So this is distance. Okay, and then it comes back, and then another portion gets reflected, and it gets smaller and smaller, then another one comes back and it gets reflected. And smaller and smaller and smaller, and you actually approach to a value. And that is the steady state value. So now, but for 5t, the voltage is at the load side and the source side. Yes. So this, it is there, but the history remains on the line. That's why you add them all together. So that's why for like the source side, it's only happened over here in time. And then for the load time, that wave has actually reached the load. Can you see at 5t, what has happened? The wave that came from there at 4t has now arrived at the load, and now it's going back to the source. But it hasn't arrived yet. It hasn't arrived yet. So it hasn't changed from the value that it was. It is still this value, which is including these two and everything before, the total voltage. Do you see? So this hasn't arrived. Only at 6t, can you see, at 6t does it arrive and change it. If you're to draw that volt, if we see what's happening here, can we see that a new reflection arrives at the source every 2t? At 0, it changed. At 2, it changed when 1 arrived. At 4, it changed. At 6, it changed. So if you're to draw the voltage of load, the voltage, I mean, of source, with respect to time, okay, you'd know at 0 something would happen. Okay, that would be V0. Then we'd know that this would be 2t, because at 1t, it's reached the load. It hasn't come back. At 1t, it has reached the load. It hasn't come back. 1t. It's still this value. It can only change when that reflection returns. That's at 2t. So then at 2t, over here, we get a change. What does it become? This becomes V0 plus by the load reflection coefficient times by V0. So you'd know that the change in here to here is V0, this amount. That's the difference, plus by that. Then, okay, so now that would be 3t. So in time over here, nothing has happened. In 3t, it's hit the load, you see. And then only at 4t, it will arrive back at the source. Okay, so then at 4t, it will arrive back. And now it will have a slightly more value, because now it will be 2 reflection coefficients. And now it will be V0 plus by, let's see what has happened. At 4t, okay, over here, that's 4t. We've had V0, we've had this one, we've had this one, we've had this one, and we've had this one. So since 2t, oh no, did I do 2t? This isn't 2t, I did wrong with this one's not meant to be. That's what it would be at the load. At 2t, it would be all of these that I'm circling in orange. This is 2t. 1, 2, 3. You see. So it would be, this one would become V0 plus by L V0 plus by LS V0. Can you see? Then at 4t, it'll be everything I'm circling in purple. It'll be this one, it'll be this one, it'll be this one, it'll be this one, and it'll be this one. I know it's a big mess now, but now you have to include both of these. Do you see what I'm drawing there? So now you'll get an additional. It'll be everything that it was before, but now plus by these two new ones, this one and this one. V naught L squared S plus by V naught L squared S squared. And then that will be the value of this one. Do you see? Do you understand? Okay, I'm glad. It's quite hard to articulate this. Okay, I'm glad. I'm very glad. It's not exactly the easiest thing to see, but it's that same, really, that concept of that you have to add both of them. Okay, I'm going to call it here because I actually really need to go. Good luck, guys. Please prepare for next week's TUT. We'll do 3-phase. Get all your questions going. Try to understand that. Really read that green book. Don't be intimidated. Just read it. If there's a point you don't understand, just take a while, digest it. Don't get lost. Don't continue reading either. Maybe continue reading a bit, but don't forget that point where you lost your focus, because you'll just come back and you'll maybe it will give a bit of context a bit further on, but don't, if it's a whole, if you carry on reading, often you'll just actually start reading things faster and faster and skimming, and then you'll start looking for formulas, and then you actually will never understand. So yeah, just go through it. You'll see that green book looks intimidating, but it's actually just explaining things in a nice way. And with your maths understanding, you'll be able to get it. So good luck, everyone. Good TUT, and yeah, have a good Friday for the rest of Thursday and a good weekend. Bye-bye.